All right, so next we're going to start talking more about the math behind the kinematics. In this case, we're going to start by talking about the acceleration due to gravity. And it turns out the acceleration due to gravity of any object near the surface of the Earth is equal to 9.8 meters per second squared. That's assuming that gravity is the only thing that's affecting its motion, so we're ignoring anything else, like air resistance, for example. And it's given the variable lowercase g. Lowercase g is the acceleration due to gravity, and it's always in the downward direction, right? Because gravity always pulls down. So there are certain problems that we can solve using that fact in one dimension, and those problems are called free fall, where free fall just means that the object is only moving in one dimension, that's up and down in this case, and it's only being affected by gravity. Nothing else is affecting its motion, it's not being pulled or pushed on by anything, and there's no air resistance. So if we want to calculate the position of an object over time that's been thrown straight up, then we would use the position equation. In this case, since it has constant acceleration, we can use the algebraic form. We don't have to use the calculus that we learned about. So the position y of t is equal to the initial y position plus the initial velocity times t plus 1/2 times the acceleration in the y direction times t squared. So in this case, the acceleration in the y direction is equal to negative g, because normally you would define up as the positive direction. So if up is the positive direction, then down is the negative direction. So the acceleration in the y direction is negative g. So we can plug in our known values now. Y as a function of time is equal to 0, because that's the initial position 0, plus 6 times t, because the initial velocity is 6 meters per second upwards, plus 1/2 times negative g times t squared. And then if you plug in 9.8 as the value of g and simplify the equation, the position y of t is equal to 6t minus 4.9t squared. And this equation describes the motion of this ball, or whatever it is, as it moves through the air until it lands. Once it has landed, gravity is no longer the only thing affecting it, so this equation is not valid anymore. So we can also talk about how to calculate the position over time when the acceleration is not constant. So for example, if the acceleration is equal to some function of time. So if that's the case, if a is a function of time, then you have to use an integral. You cannot use the algebraic equation at all. And so I'll go through the math real quick to show you what happens if you try to do that. So if we say that the acceleration is equal to t plus 1, we might be tempted to plug that value in for the acceleration in the algebraic equation. So we can do that and then factor out all the variables and distribute and all that, and get this result here, where we have the position as a function of time is equal to the initial position plus the initial velocity times time plus 1/2 t squared plus 1/2 t cubed, right? Because t plus 1 gave us two terms there. But now let's do this using the integrals instead. That takes two steps, because first we have to integrate to find the velocity and then integrate that again to find the position. So the first step is that the velocity is the integral of the acceleration, and this is a straightforward integral. It's 1/2 t squared plus t, and then plus a constant of integration. And in this case, that constant of integration is the initial velocity. And we can then integrate this again. We can plug this in for the velocity. Position is equal to the integral of the velocity. And again, it's a straightforward integral, although there are a few terms now. The position then is equal to 1/6 t cubed plus 1/2 t squared plus the initial velocity times time plus the initial position, where the initial position is the constant of integration from that integral. And you'll notice here that most of this is actually the same, except that the t cubed term is different in the two equations. The t cubed term for the integral method was 1/6, and it was 1/2 for the algebraic method. And basically what this is going on here is that in the algebraic method, it does not account for the fact that the acceleration is changing. So it's not an accurate way to do the math. We have to do the integral. The integral version is the correct result.